What's going on, everybody? It might be exam time wherever you are, so let's play a game to see how ready you are and what topics you need to spend more time on, okay? So what we're gonna do is I'm gonna post a question. You're gonna pause the video, take between 5 to 7 minutes to do each of the problems, and then hit play on the video and we'll go through each of them step by step, okay? So, number one, pause the video and give yourself between 5 to 7 minutes. Awesome. So when we're working on number one, we are given the position function, s of t, and we're just asked to plot the function. So what we can do is make a table, right? So in terms of our table, we can have one column for our input values, another column for the output values, okay? It'll look like this, and we know that this is gonna create coordinates that we can use to plot on an XY graph. And so in this case, we're plotting on an interval from 0 to 3. So t is going to go from 0, 1, 2, and 3. And so when you evaluate this function, 2t squared plus 5 at 0, that's going to give you an output of 5. When you evaluate t is equal to 1, you're going to get 1 times 2, which is 2, plus 5, which is 7. When you evaluate at 2, that's 2 squared, which is 4, times 2 is 8, plus 5 is 13. And then when you evaluate at 3, 3 squared is 9, times 2 is 18, plus 5 is 23. And so for 1a, we're going to plot the points 0, 5, 1, 7, 2, 3, and 3, 23 on this XY plot, or in this case, on this t, s of t plot, okay? So that's 1a. 1b is asking you for the velocity at t is equal to 5. And so we know that, let me label these, we know that the velocity is just the derivative, in this case, with respect to time, of our position function. And so, since we know our position function is 2t squared plus 5, we know that we need to distribute our derivative to every term in this expression. And using the power rule, the derivative of the first term, 2t squared, is just going to be 4t, plus the derivative of the second term is 5, which is a constant. And we know that the derivative of a constant is 0. And so we determine that our velocity function is equal to 4t. We're not done yet though, right? Because we need to evaluate at t is equal to 5. So we're going to evaluate the velocity function at t is equal to 5. So wherever you see t, replace it with a 5. So 4 times 5 ends up being 20. And when it comes to velocity, meters per squared, is going to be the unit. Moving on to C. So C is asking for the acceleration at t is equal to 5. And we know, similarly, that the acceleration is just the derivative, in this case, with respect to t, of the velocity function. Okay? So we determined in the previous step that the velocity function is 4t. So all we're doing is taking the derivative with respect to t of 4t. Using the power rule, that's going to be 4, and the units of acceleration are going to be meters per second squared, okay? And that's going to be your acceleration function at t is equal to 5, and this is equivalent to your general acceleration function because the t was derived out, okay? And so, moving on to number 2. Go ahead and pause the video, 5 to 7 minutes. Awesome. So, when you're looking at limits again, the limit as x approaches infinity of the function 3x squared over 10, if you were to evaluate x at infinity, or a very large number, the numerator of this function is going to get to some very large number. It's going to grow to some large number infinity divided by 10, which is just a negligible number in this case. As this gets larger and larger, your function is going to get larger and larger, and it's eventually going to approach infinity or some really large number. In B, the limit as x approaches infinity, or a very large number, of the function 20x divided by e to the 2x. And so in this case, if you were to evaluate x at infinity, this is going to give you a large number up top, and e to the 2x evaluated at x is equal to infinity is going to give you another very large number. So you get infinity over infinity. Sorry about that. Because we have infinity over infinity, we know that we're going to end up using a L'Hopital's rule to take the derivative of the top and the bottom respectively. So derivative of the top, or 20x, is just going to be 20 based on the power rule. The derivative of the bottom is going to be 2e to the 2x based on the chain rule, okay? And so now when you evaluate the limit as x approaches infinity of 20 over 2e to the 2x, the bottom is going to approach a very large number, and eventually as this gets larger and larger, it's going to bring your entire function towards 0, okay? Part C, the limit as x approaches infinity of e to the 5x divided by x squared. Again, if you were to evaluate at x approaching some large number, you're going to get infinity over infinity. Again, because we have infinity over infinity, and similar for 0 over 0, we're going to use L'Hopital's rule. And we're going to take the derivative of the top and the bottom, respectively. So the derivative of the top is going to be 5e to the 5x based on the chain rule, divided by the derivative of x squared, which is just 2x. Again, if you were to evaluate at x approaching some very large number, you would again get infinity over infinity, and you can then again apply L'Hopital's rule. Now, let's take the derivative of the top and the bottom, respectively. So now the derivative of the top is now 25e to the 5x divided by the derivative of the bottom, which is just going to be 2. So now when you evaluate the limit as x approaches a very large number, the top will approach some very large number, infinity. The bottom will be 2. And as the top grows larger and larger, the function will approach a larger and larger value, eventually getting to infinity. Okay? Now, the limit as x approaches 2 for the function x squared minus 4 over x minus 2. Now, if you were to evaluate x at 2, 2 squared is 4, minus 4 is 0, over 2 minus 2 is 0. In this case, you have 0 over 0, similar to infinity over infinity. In this case, you can use L'Hopital's rule, okay? And you can take the derivative of the top and the bottom respectively. Sorry about that. Derivative of the top is going to be 2x over the derivative of the bottom is going to be 1. Now you can evaluate x as it approaches 2. So 2 times 2 is 4 over 1, which is going to give you 4. Here, the limit as x approaches 5 of x squared plus x minus 30 over x minus 5. When you evaluate at 5, this is going to give you 5 squared, which is 25 plus 5, which is 30, minus 30 is 0. X minus 5, that's going to give you 0 over 0. Again, you're going to use L'Hopital's rule. So the derivative of the top, respectively, is going to be 2x plus 1 over the derivative of the bottom, which is just going to be 1. Now when you evaluate x at 5, 2 times 5 is going to be 10, plus 1 is going to be 11 over 1, which is going to be 11. Okay. Here, the limit as x approaches 4. If you plug in a 4, it's going to give you 0 over 16 minus 8 is 8, minus 8 again is 0. So this is another 0 over 0 case. Okay, so L'Hopital's rule again. Derivative of the top is going to be 1 divided by the derivative of the bottom, which is going to be 2x minus 2. Evaluate that as x approaches 4. 1 over 2 times 4 is 8, minus 2 is 6. This is going to be 1, 6. Okay. Number 3. Go ahead and pause this and take between 5 to 7 minutes. Awesome. So when we're given our curve for our original function f of x, we said in order to draw the corresponding curve for f prime x, we are essentially going from plotting x versus y to x versus the slope at the various points along our function. Okay? And we said the first thing we're going to do is we're going to choose places where our slope of the tangent line is 0. So in this case, the peak, this pit, and this peak, where the slope is 0. So let's call this conceptually some point A. Let's call this some point along x called B. Let's call this one C. Okay? So over here, if we approximately space this out, let this represent point A, B, and let this represent C. And so at these points, the slope, or m, is going to be 0. Now let's check to the left and right of these points. To the left of A, the function f of x is increasing, meaning the slope is going to be positive. Okay? And so let's just eyeball it and assume that the slope here is approximately 1. So let's assume it's going to be 1, and 1 is going to be some positive value up here. Okay? So right before A, the slope is going to be positive. Between A and B, the slope, the trend is decreasing. It's falling, meaning the slope is negative. Okay? So it's going to be negative between A and B. So it's going to be negative. Let's just eyeball it somewhere along here. Okay? Now, between B and C, f of x is increasing, meaning the slope is increasing, and it's positive because your trend is going up. The rise term is positive, and so between B and C, it's going to be some positive value. And then after C, it's going to be a negative slope because your trend is falling. It's not rising, but it's falling. So it's going to be negative. And so when you connect these lines, it looks like this. All right, so this is your approximate f prime x curve for this f of x curve. Okay. Part B, same thing. Let's pick the points first where the slope of the tangent line is going to be 0 because there's 0 rise, right? And so again, let's keep this basic and call these x coordinates, or x points, A, B, C. Let's call this one D, and let's call this one E, okay? So we have, I'm gonna try to evenly space it out so that it makes sense. A, B, C is closer to there, B, and E. So let's call this A, B, C, D, and E. And at all of these points, the slope, the m, right, the rise over run is going to be 0. And now let's check on the left and right of these. On the left of A, f of x is decreasing, so your slope is negative. Let's assume that it's some negative slope down here. We're approximating, right? Between A and B, f of x is increasing, meaning your slope will be positive. So some positive slope value up here. Okay. Between B and C, it's decreasing again. So between B and C, you're going to have some negative slope. And then similarly between C and D, it's going to be increasing, so you're going to have a positive slope. And then between D and E, you're falling. F of x is falling, so it's going to be negative. And then afterwards, after E, your function is increasing again. So you're going to have some, oh, after E, sorry about that, not on E, but after E. Okay? So at that point, so when you connect all these points, it's going to look like this. Okay? So that's your approximate f prime x curve for this f of x curve. On C, same thing. Let's first pick these points where the slope of the tangent line is 0 because there is no rise term, because slope is rise over run, right? So at these points, we're going to call these very similarly A, B, C, point D, E, F, and G, okay? So we have A, B, C, D, E, F, and G. C, D, E, F, G. Who needs hooked on phonics, right? We got plotting. So the slope is 0 at these points, again, because the slope of the tangent line at these points is 0. And then let's check what the trend looks like before and after these points. So before A, your f of x is increasing, so you have some positive slope. Between A and B, it's decreasing. Between B and C, it's increasing. Between C and D, it's going to be decreasing, so it's negative. Between D and E, it is increasing, so it's going to be a positive slope. Between E and F of x is decreasing, so your slope is negative. Between F and G, you're increasing, so you have a positive slope. And after G, this is falling, so you have a negative slope. So similarly, when you connect all these lines, this will be your approximation for the curve of f prime x based on this f of x. All right, number 4. 5 to 7 minutes, and then come back. Awesome. So if you're looking to determine the equation of a line, right? Whenever you see equation of a line, we think of the point slope formula, which is y minus y1 time is equal to the slope m times x minus x1. And so in this case, the first thing we're going to do is determine our slope, right? Slope is rise over run. So slope, and we thought of as rise over run, or change in y direction, the vertical direction, over change in the horizontal direction, okay? And that also looks like this. So all of these are equivalent. And let's use this one because we conveniently have 2 sets of coordinates. And so B will be y2, x2, y2, A will be x1, y1. Okay, so y2, 11 minus y1, 5. 11 minus 5 over x2, 10 minus x1, 8. 10 minus 8. That's going to give us 6 over 2, which is equal to 3. So from this, we determine that our slope is equal to 3. So we have our m. x1 and y1, just pick one of these coordinates to use. So let's pick point A. So y minus y1, which is 5, is equal to our slope, which we determined as 3, times x minus x1, which is 8. Now we just have to simplify. So y minus 5 is equal to 3x minus 24. Move 5 to the right. Y is equal to 3x minus 19. Okay, so this is the equation of the line passing through points A and B. Okay? number 5. 5 to 7 minutes. Awesome. So we're looking at evaluating derivatives. So based on the power rule, this is going to end up being 4 times 5, which is your new coefficient 20. Leave that base, subtract 1 from the exponent. 4 minus 1 is 3. Okay? Similarly here, you're going to use the chain rule here, right? So the derivative of e to the something is equal to e to the something, right, times the derivative of that something. In this case, that something is 5x to the 4th. Okay, and so in this case, this is going to be e to the 5x to the 4th times, based on the power rule, 4 times 5 is 20. Leave your base, x, subtract 1 from the exponent. So your final answer will be 20x cubed times e to the 5x to the 4th. Okay? And this one was 20x cubed. Part C, sine of e to the x, again, chain rule, okay? The derivative of sine of something is equal to cosine of something multiplied by the derivative of that something. In this case, the derivative of something is the derivative of e to the x, which is just e to the x. Okay, so this is going to end up being cosine e to the x times e to the x, which ends up being e to the x, cosine e to the x. All right. Part D, e to the sine x. Chain rule, okay? Derivative of e to the something is equal to e to the something, so e to the sine of x multiplied by the derivative of that something. In this case, that something is sine x, which we know this is just cosine x. So this is going to be equal to e to the sine x multiplied by cosine of x, which gives us cosine of x times e to the sine x. Okay. Last one, 2x squared times cosine x. So this derivative, you're going to use a property, right? So derivative with respect to x, in this case, of 2x squared cosine x. I'm going to write this one out so you can see it. The 2 is a coefficient. It is just a number. It is a constant. With a constant, you can move that out in front of the derivative and multiply it back in later. So you actually have 2 times the derivative with respect to x of x squared cosine x. X squared can be looked at as your f of x. Cosine of x can be thought of as your g of x. Based on this, you're going to use the product rule. So you're going to have 2 times f prime g, which is f prime, which is going to be 2x times g, plus g prime, derivative of cosine, f, which is x squared. Okay? And so this is going to end up looking like this. 2 times 2x cosine of x minus x squared sine of x. Okay, and then when you finalize this, it's going to be 4x cosine of x minus 2x squared sine of x. Okay. Awesome. Number 6, 5 to 7 minutes. All right. So when you're looking at word problems, we said you need to pick out the information that you're given, and you need to figure out what you need to find. Okay. So in this case, a zookeeper wants to build a rectangular petting area. So from here, you should have seen a rectangular area, and you know that if we draw out a rectangle, right, these two sides will match. these two sides will match. We know that the area of this rectangle is going to be x times y. Okay? As a zookeeper wants to build a rectangular area and has access to 5,000 feet of fencing. What are the dimensions of the fence that will create the largest petting area? Based on 5,000 feet, we know that the length of all four of these sides are going to equal 5,000 feet because that's all the zookeeper has. So based on length, when you add up all these sides, 2x plus 2y, that's going to equal 5,000, or the amount of fencing you have. So in this case, what are the dimensions of the fence that will create the largest area? Largest area. So here you're trying to maximize the area, okay? You're trying to maximize this function over here. So we're not going to mess with this initially. We're going to modify our length equation and then plug back in. So in here, we're going to solve for our y term in terms of x. So 2y is equal to 5,000 minus 2x divided by 2. Y is equal to 2,500 minus x, okay? Now that we have y as a function of x, we're going to plug that back into our area equation. So now we have area equal to x times 2,500 minus x. And now we have area in terms of a function of x is equal to 2,500x minus x squared. This is the function that we want to maximize, okay? And so to maximize this, we're going to find the derivative, f prime x, and set it to 0. So the derivative of the right-hand side of this is going to be 2,500 minus 2x is equal to 0. Solve for x. So move 2x to the other side, you get 2x is equal to 2,500 divided by 2. X is going to be 1,250, okay? 1,250 feet, okay? Now that we have these sides, let's plug x back into our length equation to figure out y. So now y is equal to 2,500 minus 1,250, which ends up being 1,250, okay? And so you have dimensions of x and y to maximize the area. All right, number 8. Awesome. So when you're looking at sigma notation, sigma just represents summations, or you're going to add up a bunch of terms. In this case, you're going to add up this function evaluated on the interval from 0 to 4. So in this case, this is just equal to wherever you see an n, plug in a 0, 0 squared, plus wherever you see an n, put in a 1, 1 squared, plus 2 squared, plus 3 squared, plus 4 squared. From 0 to 4, 0, 1, 2, 3, 4. Add this up, and this is going to give you the final number answer that you're looking for. Similarly here, I going from 2 to 5 of this function, okay? So you're just going to add up this function evaluated at values of I ranging from 2 to 5. So 2, replace I with the 2. 2 times 2 to the third, plus 2 times 3 to the third, plus 2 times 4 to the third, plus 2 times 5 to the third, right? So from I starting at 2, ending at 5, evaluating this function at every point in between. And when you add this up, this will give you the single value answer or solution you're looking for, okay? Here is the opposite. We're looking for patterns. We write the following patterns in sigma notation. And so here you can see that 1 over e to the x, 1 over e to the 2x, 1 over e to the 3x. And so in this case, the pattern is not in the top, right? And so let's rewrite this. Let's rewrite this 1 so we can compare. So if you're re-looking at this, this is the same thing as 1 over e to the 0x, right? Because e to the 0, 0 times x is 0. E to the 0 is 1. 1 over 1 is just 1. The next one down is 1 over e to the 1x, right? And then you have 1 over e to the 2x, 1 over e to the 3x. The only values that are changing are in this denominator exponential, okay? And so you can generalize this as 1 over e raised to some number multiplied by x, okay? Now that you have your function, what is the interval that this thing is evaluated over? This is going to be starting at 0, at n is equal to 0, ending at n is equal to 3, because 0, 1, 2, 3. Okay? So part B, and this is going to be your function, your sigma notation, sorry about that. Looking at B, here you have a different, more difficult pattern. So e to the 4x over cosine 6x, e to the 6x over cosine of 9x. It doesn't seem that clear, but you're going to notice that essentially this is going to be e times the similarity between 4 and 6 is a 2, right? So in this case, this is going to be 2 times 2 times x, which is 4x, over cosine of 6 is 2 times 3, 2 times 3 times x, right? The next one down is e to the 2 times 3 times x, 2 times 3 times x, all over cosine of 3 times 3 times x. The last one is going to be e to the 2 times 4 times x, right? 2 times 4 times x over cosine of 3 times 4 times x. 3 times 4 times x. Okay? So now that we're looking at this, the only number that changes up here is 2, 3, 4. Down here, the only number that changes is 2, 3, 4, right? And so here you can say that the pattern is going to be e to the 2 times some number times x, right? Divided by cosine of 3, right? 3, 3, 3 times some number times x, right? So this is going to be your pattern now, or your function. What's the interval that this thing exists over? This thing starts at 2, 3, 4, so it starts at 2, ends at 4, right? So n is equal to 2, ends at 4. So you were able to catch that. Really good job, okay? This one was a little bit harder. Number 9, give yourself some time and then come on back. All right, so when you're evaluating integrals, in this case definite integrals because you're given an interval, right? Using Riemann endpoints, left and right are going to determine what your sample values for x are. So we said that you can calculate delta x for the change in bars by this equation, x, delta x equal to b minus a over n. N is the number of subintervals you want. So b in this case is 3, a in this case is negative 3. So 3 minus negative 3 divided by 3, okay, which is 6 over 3, which is 2. So we know that our delta x value is 2. And since we're using the left-hand endpoints, the left hand is going to start with negative 3, right? So our sample points are going to be negative 3 plus 2 is going to be negative 1 plus 2 is going to be 1. So these are going to be our 3 subintervals because n is equal to 3. And so we're going to evaluate like this. So this interval, negative 3 to positive 3 of x squared dx, this is going to be equal to our delta x value multiplied by, right, our function evaluated at all of these points. And so that's going to look like this. Delta x, which is 2, multiplied by negative 3 squared, right? Because our function is x squared, plus negative 1 squared, plus positive 1 squared. And when you multiply what's inside the bracket and multiply by 2, this will give you your numerical answer, okay? Similarly, let's look at this one, okay? So using the right-hand endpoint, we know that we can first calculate delta x, our Riemann steps, right, by b minus a over n, which is going to be 2, which is b, minus negative 2, which is a. So 2 minus negative 2 divided by n, which is 4. Because we have 4 subintervals. 4 divided by 4 is 1. So our delta x is going to be 1. Given that, our sample space or sample inputs are going to range from negative 2. Add 1, it's going to be negative 1. Add another, it's going to be 0. Add one more, it's going to be positive 1. Okay, and now you have 4, 1, 2, 3, 4 samples to represent your 4 subintervals. So now same thing. This interval from negative 2 to 2 of x to the 4th plus 2 dx is going to be equal to your delta x multiplied by the summation of your function evaluated at all of your sample inputs. So this is going to be 1 times negative 2 to the 4th is negative 2 times negative 2 is 4 times negative 2 is 8. 4, 8, 16. That's going to be 16 plus 2, which is going to be 18. Okay? Or actually, let me write this just so you can see it. You have negative 2 to the 4th plus 2. So that's your first sample. You're going to add that to this, negative 1 to the 4th plus 2, plus you're going to have 0 to the 4th plus 2 plus 1 to the 4th plus 2. And again, when you evaluate what's inside the bracket, multiply by 1, that will be your numerical answer. Okay? Last one, number 10. Give yourself between 5 and 7 minutes to do this, and then come on back. So, using the mean value theorem, we know that there exists some function or some value c that fits this, right? fb minus f of a over b minus a. So what we're saying is there is some value c that exists along the interval a to b between 0 and 2 that fits this description. So let's figure it out. In this case, a is 0, b is 2. So we'll start filling this thing out, right? So this function evaluated at 2, or b, is going to be 2 squared, which is 4, times 10 is 40, plus 2 is 42, minus this function evaluated at a, or 0. This is just going to be 2, divided by 2 minus 0. So this is going to end up being 40 over 2, which is 20. Okay, so now we have f prime c is equal to 20. What this means is the derivative of this function, right, evaluated at c. So let's find that. This is the derivative of this function is 20x, right, plus 0, because the derivative of 2, a constant, is just 0. So you have f prime x is equal to 20x. When you evaluate this thing at c, plug in c for this. So this evaluated at c is equal to 20c. Okay, let's put this back into this equation. So now we're going to have 20c is equal to 20, right? Because our f prime c is 20c is equal to 20. So now we can simplify for our value of c, which is 1. And we can sanity check because 1 is between 0 and 2. Okay? So that's all I have for this video. If you were able to get through a lot of those problems, then good job. You're on spot approximately. And so, but if you were struggling a little bit based on the questions that you were struggling on and that you got incorrect, go back and look at those specific topics. Okay. So if you have any questions or comments, please leave them below. If not, then thank you. This was the time challenge exam practice.